let's look at the next part. So we finish up molten already. So molten is quite simple. The only anion will change to product. The only cations available in the molten form, which is the lead-2 ion, will change to the product. Okay, so we are not going to have a complicated scenario. But when we come to aqueous electrolytes, so it is going to be much more complicated already because of the presence of water. So first of all, we have to understand how water affect. Okay, how water affect. So I'm going to write down a few equations from the water itself. So the first equation that I'm going to write here is at the cathode there. You know, cathode is where the cation stick to it. Okay, the cathode, you can see here, cathode is where the cation, the positive ion, stick to it. So when we use aqueous, right? So first of all, we need to know aqueous means water. Water tend to break down to H plus and OH minus. Okay, so that means we also have these cations, the H plus, that go to cathode. So there are two cations that go to cathode now. One is from the compound that is inside the electrolyte. Okay, the other one is the cation from the water. Okay, so that's why we need to know the equation. We need to know the equations for the H plus. So for H plus, right? So I write down here. H plus, take electrons, become H2. Okay, so we need to know the voltage also. So let's see the voltage. This value. So it is 0.00 volt. Okay, at the anode. So anode, again, anode is where the anions stick to. Okay, so for molten we have only one choice, but for aqueous we have hydroxide as well. So hydroxide, we have to know the equation. So the equations for the hydroxide is given here. As you can see, what happened at cathode is we refer to, okay, so this is the one. This is the one. Okay, so why we have to take this one? Because you have to know that hydroxide at the anode there is going to oxidize. So it's going to oxidize. Oxidize means that will go backwards. They will go backwards from hydroxide, oxidize to this, and this. Okay, three products. Okay, so we have to go backwards. So let's say I write down this equation first. This equation, okay, from data booklet, we have O2 plus H2O plus electron become OH minus. Okay, then we balance the equation. 4, 4, 2. Okay, we balance the equation. The voltage given is positive 0.40 volt. So positive 0.40 volt. So this is what the equation given. Always remember, data booklet give us equation in reduction form. So from left to right, it is reduction. But what happens at anode is oxidation. So you have to read from hydroxide to the left. Okay, to the left. So they give reduction form. But what happened at anode is oxidation. So if it's oxidation, right? So basically what to do is, if it's oxidation at anode, we need to swap the equation. start with hydroxide, form O2, form 2H2O, and form 4 electrons. And when you swap the equation, right, the E theta just now will change sign. Will change to negative 0.40 volt. Okay, that will change sign when you swap the equation. Okay, so that is what actually happened at the anode. Hydroxide changed to O2, changed to water, and 4 electrons. Okay, now let's look at the theory here. So when we look at the theory here, we have to take one example at the same time. Okay, one example at the same time. So I will set one example so that later when you look at the theory here, you can understand it easily. So let's say I put somewhere here. Okay, so my electrode and my electrolyte. So my electrolyte is going to be, let's say, zinc chloride, aqueous, dilute one. Okay, so I'm using aqueous here. Now the battery. Okay, so let's start from the beginning. First, when we see the battery terminal, the longer line represents positive terminal. So because of that, here is positive. So this is the anode. This is the anode. Anode stay on the left. And then negative terminal is on the right. So the electrode is cathode. So cathode is negatively charged. Anode is positively charged. So anode attract negative ions. So the negative ions available are chloride, Cl minus, and hydroxide. Okay, so maybe I just write somewhere at the bottom instead of squeezing all the information there. Okay, so now let's say I just remove everything from there, and okay, so I put like this. The N ion available are chloride and hydroxide. The cation available are zinc 2 plus, and H plus. So of course the H plus and the OH minus come from water, like what I mentioned just now. So okay, since you have two N ions available and two cation ions available, so we need to know which one is chosen to form element. Okay, which one is chosen? Are we going to choose, for example, for the N ion side, are we going to choose chloride or hydroxide? So there is a way to decide that. On the cation ion, are we going to choose zinc 2 plus to form elements or choose H plus to form elements? There is also a way to decide. So let us start from the cation ions. Okay, start from the cation ion. To know which one is going to be chosen to change to its element, so we have to look at the E theta. So we look at data booklet first. Okay, so data booklet on the first page again. So I write down the equation here. For zinc 2 plus 2 electron become zinc. The E theta is negative 0.76 volt. Okay, so the H plus I already wrote down. It's up here. This is the equation. So H plus 2 electron become H2 0.00 volt. Okay, so now which one are we going to choose? So we have to take it in this way. It depends on the E theta actually. Okay, it depends on the E theta over here. Whoever having a more positive value, okay, remember this, whoever that is having a more positive value means there is a higher tendency for the reaction to react forward. Okay, forward reactions can happen more easily, in other words. So for example, 0.00 volt is more positive compared to negative 0.76. So which means H plus is more likely to have forward reaction compared to zinc 2 plus. So this is more likely to go forward. So because of that, cathode is where reduction happen. So reduction means go forward. So H plus has the higher tendency to go forward because the E theta here is more positive. So we choose this one. Okay, we choose H plus to form product. Okay, so choose this because it's more positive, more likely to move forward. So we have to look at the E theta, the voltage. Okay, we have to look at the E theta to decide which one is chosen. Okay, so that means out of the two choices here, what happened at cathode is the two go to the cathode, but at the end, who receive electrons? So H plus receive electron and form H2. So the observation at cathode is effervescence, or maybe you can say gas bubbles are formed. H2 are gas, so gas bubbles are formed. So we choose this. That is how we decide. Okay, so that is what happened at cathode. Now you look at the theory here. If the E theta of the metal, normally the cation are metal, if the E theta are more than 0, okay, our case here is less than 0. So we look at less than 0 first. If our E theta is less than 0 for the metal, for the metal ions, for the zinc ion here, then metal more reactive than hydrogens. So the more reactive one we don't choose. We choose the other one. We choose H plus. We choose H plus to form H2. Okay, so this is a way to explain it. But if you follow the way that I said just now, right, just choose the one that is more positive. Okay, whoever that is more positive, just choose it. Then it's easier. Okay, so this is another way to take it. If it's less than 0, you don't choose the metal, but you choose H plus. Okay, so that is what they said, which is similar. Same idea with this one. If let's say I give you one more example, I use blue color. Okay, I don't use zinc chloride now. Let's say I use copper to sulfate, aqueous. But my electrode is not carbon. Okay, let me label it. My electrode is not copper. My electrode is not copper. If my electrode is copper, I follow this way, reactive electrodes. So my electrode here is just, let's say, carbon. It's just carbon. Okay, so we don't have a reactive electrode here. Okay, so if I use copper to sulfate as my electrolyte, so my cation is now Cu2 plus and H plus. H plus we already know it is 0 volt. Copper 2 ions, let's take a look. We write this down. Cu2 plus 2 electron becomes Cu. That is positive 0.34 volt. Okay, now you use the same idea again. Okay, out of Cu2 plus and H plus, which one are we going to choose? We have to choose the one that is more positive. You see, this is more positive. This is positive 0.34. This is 0.0 volt. So this is more positive, more likely to move forward, more likely to reduce. Okay, so that means in this case, if our case is copper 2 sulfate, we have these two choices, and at the end, we have to choose copper 2 ion to reduce. So we choose this. Okay, we choose this. So for the blue color case, we have to choose this to discharge. Choose this to discharge, that means Cu2 plus change to copper. So choose the more positive one. Okay, so you see the note. The note here, they are using, okay, you may refer to the first point at the cathode here. So E theta greater than 0 for the metal ion. So example is copper 2 ion, more than 0, this one, 0.34, more than 0. So if it's more than 0, then metal less reactive. Metal less reactive than H. Metal less reactive. So how are we going to take it? You know, they tend to go forward. They tend to go forward to form copper metal. So that means this metal tend to remain as metal instead of becoming ions. So they tend to move forward. So that means copper atom or copper metal is not reactive, less reactive. So if they are less reactive, then H less reactive than hydrogen, then metal form. So which means when you compare this and this, so at the end, what are we going to do is we take Cu2 plus to form product. Okay, so they are using slightly different way to let you decide. So my suggestion, just choose the one that is more positive. Whoever that is more positive, just choose it to form product. Okay, now we settle cation already. Okay, so we look at N ion or the anode side. So if I follow the red color example, as in here, the red color example, zinc 2 chloride. So we have chloride from the compound, and we have hydroxide from water. So let's look at the E theta first. The E theta. So when you look at the E theta, right, at the same time, you need to know, let's say, so I write down the equation. So chloride, oops, okay, I use red color first. This one is zinc 2 chloride, our discussion now. Okay, chloride change to chlorine. Okay, so maybe put more space so that I can put the voltage. So chloride change to chlorine plus 2 electrons, so balance, and negative 1.36. Negative 1.36. Hydroxide, I already swap over here. So hydroxide, so let's say I write down here, hydroxide, as you can see on the right upper corner, somewhere up here, right upper corner, I already write down the equation. So I just put together only. So hydroxide become O2, 2H2O plus 4 electrons, and the E theta is negative 0.40 volt. Okay, so you can see two situations. Chloride, negative 1.36. Hydroxide, after you swap, negative 0.40. We swap already because anode is where oxidation happens. So the data booklet give equation in reduction form. That's why we need to swap, and at the same time we swap the E theta. Okay, after you swap, right? So we decide which anions to be chosen by using the same method. Okay, so whoever that is more positive is more likely to go forward. That is the concept. So if you compare minus 1.36 and minus 0.40, so we can say that the hydroxide is more positive. more positive. So we choose hydroxide. Okay, so we choose this. Okay, we choose this. We choose hydroxide, and at the end, what happens at anode is we follow the second equation. Hydroxide change to oxygen, water, and electron. So the observation is colorless gas bubbles at anode, which is due to oxygen. Colorless gas bubble is observed. Okay, so that is how we decide. The product. Let's see the notes again. Okay, let's see the notes. So the note say, as you can see here in the table, the right hand side, E theta more than 0.4, more than 0.4. Okay, so the notes never swap, okay, so by right we have to swap because oxidation really happened. So if your E theta is more than 0.40, this is where before it swap. Before it swap, it is positive 1.36. Imagine that they are approaching it by using different way. Positive 1.36. This is positive. Okay, this is, imagine before you swap, the hydroxide is positive 0.40. Okay, before you swap, and before you swap, this is positive 1.36. So the note here is talking about the situation before you swap. Okay, so the E theta is more than 0.4. It refers to chloride. Chloride is positive 1.36. Okay, then non-metal less reactive than hydroxide. So it refers to chloride. The chloride is less reactive. Okay, it's less reactive than hydroxides. So non-metals form. So non-metal less reactive. Okay, so this one is, okay, typo error there. I need to change a little bit because this statement have something wrong, so I have to change it in this way. If E theta less than, this one is more than, so I have to change it. So let's take a look again. If E theta less than 0.4 before you swap, okay, so I don't want to look at this first. I look at this. If E theta more than 0.4, this is the case, more than 0.4, before you swap is 1.36. Then non-metal refer to the chlorine here, more reactive than hydroxide. So we don't choose the more reactive one. We choose hydroxide. Okay, we choose hydroxide to form water. So they are trying to say it in that way, but I personally feel like this is a little bit confusing. Okay, so that's why I put this way before I explain that. Okay, it can be used somehow, but I rather swap and tell you to choose the more positive one. Okay, so what they say is, before you swap, whoever that is more positive, you don't choose. You choose the other one. So they are trying to say something like that. Okay, so, and this is the other way around. This is the other way around. If your E theta is less than 0.4, then you choose the non-metal to form product. Okay, so this is the other case. Okay, so it's a bit confusing for me. Okay, it's a bit confusing, the statement here. You need to think slowly. So to make it fast, my suggestion is, anode is where oxidation happens. So oxidation is where you have to swap the equation. When you swap the equation, you swap the E theta, then you compare between the two E theta. Whoever that is more positive, you just choose it. So that is my suggestion. Okay, so we settled already for this part. So by concentration, so concentration affect the product also. So how? You see, following result from above, if solution very dilute, if the solution very dilute, that means a lot of water and relatively less amount of solute. Less amount of solute. Okay? Zinc chloride is less, water is more. Okay, so because of that, H plus and OH minus are more. Okay, are more in a dilute situation. So following result from above, if solution very dilute, this occur greater. So if the solution is very dilute, like for example, very dilute. Okay, let's say one example. 0.001 mole per dm³. This is very dilute. Very dilute means very little of zinc chloride and very little of zinc 2 plus ion and chloride ions, and a lot of H plus and OH minus from water. So in that case, the note said you just choose the ions from water to form element. From water we have H plus, form element. From hydroxide, from water we have hydroxide. So we choose hydroxide to form elements, to form products. Okay, so that means if they are very dilute, then you just choose the ions from water to form product. So that is what the note's talking about. Okay, if they are very dilute. So if they are very dilute, very easy. Just choose the ions from water and form product. So which means we choose the two equation that I wrote just now. So which means we choose this one, H plus form H2 and OH minus form products. Okay, so just like that. This is the effect of concentration. We don't look at E theta already. Okay, we don't look at E theta. We just take from water, okay, and make the ions from water discharge. Okay, so the thing is, when should you use E theta and when should you use this concept? So you have to know this E theta can be used when the concentration is 1, okay, I write down here, when the concentration is 1.0 mole per dm³. 1.0 mole per dm³ is the standard concentration. We can only use E theta when the concentration is 1.0 mole per dm³. So if they are very dilute, then you can follow this idea. But if let's say they are not very dilute, they are in between, or they are very concentrated, then what should we do? Okay, if they are very concentrated, like 2.0 mole per dm³, or maybe not very dilute like this, but like 0.8 mole per dm³. So what should we do? So we will come to that later actually. So that is maybe I just let you take a quick look first. If the concentration is not very dilute and not 1.0, here. If they are not 1.0 and not very dilute, then you have to recalculate your E, your voltage, by using this formula, the Nernst equations. You have to use this formula to recalculate your E, and then you can just choose accordingly. So what I mean is, you follow back the concept that I mentioned. Whoever that is more positive, just choose it. After recalculate the new E with the concentration that is not 1.0. So if the concentration is 1.0, you look at data booklet. If the concentration is not 1.0, you recalculate the E and make decision again. Choose the one that is more positive. If they are very, very dilute, no need to count all this. Just choose the one from water. Choose H plus and choose OH minus. So the idea is like this. Okay, so it is very complicated actually. And what note just now? Okay, so we have done this part already. Choosing product. Okay, this is the qualitative part. Okay, so which ions is chosen here. Okay, so we already discussed. Now the quantitative part is about how much. Okay, you look at 2.3. 2.3, we will talk about how much. So quantitative electrolysis. So quantitative electrolysis is calculating how much products are formed. You can count the mass of the product form, or you can count the mole the product form. Calculate the quantity. Okay, so this involves some physics concept, the electricity concept. So first point, calculating quantity of charge passed during electrolysis. So this is the thing that you need to do over here. So imagine that you're doing electrolysis like this. Now, in order to do quantitative electrolysis, you need to know the current. You need to know the current. So we need to change our diagram a little bit. We need to add ammeter. So imagine that, let's say here, I add ammeter. Okay, so yeah, so I add ammeter here. Okay, so as you can see somewhere here, the ammeter. So I need to put ammeter to find out the current. So likewise, if I want to find out the mass of product form, I need ammeter for this case. So let's say I add ammeter over here. Okay, so ammeter. So we add ammeter over there so that we can find out the current used during the electrolysis. And we need to know the time also. So how long you turn on the battery, how long you turn on the battery. So to find out the time, we need stopwatch. So you take the current, multiply with the time, then you get the Q. The Q is the amount of charge. So the unit is coulombs. Okay, so the mass of a substance liberated is proportional to the quantity of electricity. That means the quantity of charge which passes through electrolyte. So it's proportional. Okay, so they are trying to say something like this. Let me write down at the side here. The mass of the product is proportional to the charge. So in other words, it means if you use higher charge, then you will get more products in terms of mass. Okay, more products. Okay, so higher charge, more product. So should be logic one. Imagine if you use battery of high voltage, a lot of electric or a lot of electrons flowing through. Of course, you should expect more products formed. Okay, if you use a very low power, very low voltage battery, and of course, in that case, less product. Okay, so this should be reasonable. Okay, so let's move on with the next point. 1 Faraday. So this capital F, 1 Faraday. So this new unit here is actually an important thing for us to calculate the amount of product forms easily. Okay, so what is 1 Faraday? You see, quantity of electric charge carried by 1 mole of electrons equal to 96500 coulomb. That is 1 Faraday. Okay, so I give one example so that you can imagine. Okay, so let's say one example. If I'm talking about zinc, let's say, just now we discussed zinc already. Okay, as you can see here, zinc 2 plus 2 electrons becomes zinc. So let's say I put it here again. Zinc 2 plus 2 electron becomes zinc. So From the equation, we can find out something like this. Okay, we can find out something like this. Let's say zinc 2 plus. Let's say I use 1 mole of zinc ions. 1 mole. Okay, 1 mole. Based on the equation, if you use 1 mole of zinc ions, then it will involve 2 moles of electrons. Then they form 1 mole of zinc atom. Based on the equation, we can see that. And the notes say that 1 mole of electrons is equal to 96500 coulomb. The charge carried, okay, is 96500 coulomb. And if you use 2 mole, okay, so 2 mole of electron, of course, logically, the charge is double. The charge is double. 2 mole of electrons is hence equal to 2 times 96500, which is equal to, okay, I mean the charge. The charge is 2 times 96500, which is equal to 193000 coulomb. So this is the amount of charge carried by 2 mole of electrons. And this is equal to 2 Faraday. 2 Faraday. So the Faraday is significant here because it makes us very convenient. It makes us very convenient in this way, imagine 2 mole of electrons, the charge carried is 2 Faraday. 2 Faraday. 3 mole of electrons, the charge carried is 3 Faraday. Of course, you have to convert Faraday to Coulomb also by multiply with 96500. Okay, so if necessary, okay, so 2 Faraday, 2 times 96500, then you can change the charge to Coulomb. Okay, so that is the usage or the significance of Faraday. You can conveniently directly link the mole of electrons to the number of Faraday. 2 mole, 2 Faraday. Okay, but remember, 1 Faraday is 96500 coulomb. So you need to convert accordingly. Okay. So we move on first. Let's see more formula. Relationship. F equal to LE. So F is the Faraday, equal to L, Avogadro constant. E is charge on 1 electron. Charge on 1 electron, this value is given. Is given as 1.6 times 10 to the power of minus 19 coulomb. Okay, this is, be careful with this. This is 1 electron. Just now, it is 1 mole of electron. 1 mole of electron. So 1 mole of electron is a lot of electrons. 6.02 times 10 to the power of 23 electrons. So that much of electron carry this much of charge. So 1 electron carry a little bit of charge on it. So it's a very small value. Okay, so what is the usage of this formula? F equal to LE. So I give one example here. Okay, F equal to LE. So example. This formula is for us to find out how much charge is carried by 1 Faraday. Okay, so as you can see, L is Avogadro constant, 6.02 times 10 to the power of 23. E is the charge of 1 electron, 1.6 times 10 to the power of minus 19. Okay, so if we press calculator for this, so you will get 96320 coulomb, which is very close to 96500 coulomb. So this formula is used to find out how much charge is carried by 1 Faraday. which means 1 mole of electron. Okay, so that is the usage of this formula. Now, example. To liberate 1 mole of hydrogen gas. So you can see 2H plus 2 electrons become H2. Okay, in other words, that means 2 mole of H plus react with 2 mole of electrons become 1 mole of hydrogen gas. So 2 mole. Like what I said, 2 mole of electron means 2 Faraday. 2 Faraday. Required 2 Faradays of electricity to form 1 mole of H2. Okay, so they are trying to tell you the idea of Faraday. This thing itself is not enough to score exam. So in order to score exam, let's see one example here. Okay, I will go through one example with you. Okay, now since I have this reactive electrode here and it's quite empty here, so I will put this as my example and you see how we do calculation. Okay, so how we do calculation. Let's say I create a question here. So again, I will add ammeter over there. Okay, so I will add ammeter here. So I can read the current. So let's say, for example, I use current equal to 0.50 ampere. And the time span is, let's say 5 minutes. So I wait for 5 minutes. The electrolysis, I wait for 5 minutes. So I want to know, from our discussion just now, I said cathode becomes thicker. So I want to know how much increase in mass at cathode. Okay, so I want to see how much increase in mass at cathode. So to do this, what we do is, you see how we make use of the formula. Basically, which formula should we use? Okay, I highlight a bit. First, you have to use Q equal to IT. Then after that, you use 1 Faraday equal to 96500. Okay, and then you use ratio. To figure out the amount of product. Okay, so we need to see example to understand better. Okay, so first, to do these questions, we use Q equal to IT. Q equal to IT, 0.50 times 5 minutes. So 5 minutes we change to second, the SI unit, 5 times 60. Okay, so we count this, 5 times 60, and then this is equal to 150 coulomb. So this is the amount of charge that involved in this 5 minutes electrolysis. Okay, so this is the first thing. Okay, I write down the step. Step 1, find Q equal to IT. Step 2, write down the equation, the half equation, to find out the mole ratio of electron and product. Okay, so this is step 2. Okay, let's see. This is our equation. Okay, we write down. Step 1. Okay, step 2. The equation is Cu2 plus 2 electrons becomes Cu. So we have to write this equation and find out the mole ratio of electrons and products. So the mole ratio is 2 mole to 1 mole. Okay? The electrons and the product, 2 mole to 1 mole. 2 mole to 1 mole. Huh? Okay, so you know 2 mole of electron means 2 Faraday. 2 Faraday. So 2 mole of electrons, the charge involved is 2 Faraday. 2 Faraday. Okay, I put it in step 3 first. Step 3. Use 1 mole of electrons equal to 96500 coulomb and ratio to find out mole of electrons involved in the current reaction. Then find mole of product. So this is step 3. You see how we use it? The theory said 1 mole of electron is 1 Faraday. 1 Faraday is 96500. Okay, this is what the theory said. Okay, so I write down first. 1 mole, this is step 3. 1 mole of electrons is 96500 coulomb. But the thing is, we don't use 96500 coulomb. We don't use this much of charge. We use 150 coulomb only. So 150 coulomb is how many mole of electrons. So we want to find this. And how to find this X here. Okay, so this one, I'm trying to draw arrow. So I draw it again. Okay, 150 coulomb is how many mole of electron. So what to do here? You see the step that I wrote here. Use 1 mole of electron equal to 96500 coulomb and ratio to find out mole of electron involved in the current reaction. Our current reaction is this reaction where we take this current and this electric current and this time, and the charge involved is just 150 coulomb. So 150 coulomb represent how many mole of electron we need to find out first. Okay, so to find out this, we use ratio to find out. Use ratio. So ratio method. So the ratio method is you take the mole divide each other, x over 1, then is equal to or is proportional to the charge divide each other. And then we get the x already. Okay, we get the x. So the x is 0.00155 mole of electrons. Okay, so we use ratio to get the x, the mole of electrons that involved in the reactions that we are discussing now. So this is the number of mole. Okay, so now you look at this part. Our equations show that the ratio of electrons to product is 2 to 1. 2 to 1. Okay, so if we use this ratio and apply it here, then we can find the mole of product. Okay, so as you see, we divide by 2 to find the number of mole of the product. So we can apply it here. We divide by 2, then we will get the mole of product, no mole of copper. Okay, so now we write it down. Mole of Cu form is equal to 0.001554 divided by 2. Okay, so again, we divide by 2 because the ratio there is divide by 2. Okay, so I try to put some arrow there. Okay, so we divide by 2, then we get 0.000777 mole. This is the mole of copper, and finally you can find the mass of copper. So mass of Cu is the mole multiplied with the molar mass. So the molar mass of copper is 60. Okay, so hold on, 60 copper, 63.5. 63.5. So we get 0.0494 gram. So this is the amount of, or this is the mass of copper that stick to the cathode after 5 minutes. Okay, so this is the amount. So we count it in this way. Okay, so it's your turn to practice. So I already talked for 1 hour plus already. So it's your turn to practice. I just pause this first. Okay, so far any question or not? No question, huh? Have you learned this in college? Oh, I see. Okay, so we try something like this first. Calculation, see whether you can handle or not. If you cannot handle, I will just explain. But I let you try first. I will send you this thing because I record down already 1 hour something. So if any part that is not clear, you just listen to it again and again until you understand. Sometimes maybe you need to listen a few times to understand it. Okay, so let's see one question first. One question involving calculation of mass.